Welcome back to Techniques in Quantum Mechanics in Physical Chemistry. My name is Kevin Tokoph. Make sure to like the video, subscribe to the channel for future videos and notifications. In this video, what we're going to do is we're going to use the Schrödinger equation, and it's the time-independent Schrödinger equation, to ultimately derive an expression for the particle in a box model. And particularly, we're looking for the eigenvalue, which happens to be the energy of a particle in a one-dimensional box. In later videos, we'll do two-dimensional and three-dimensional. So what is the deal with particle in a box? Well, essentially what it is, and it's not actually, it doesn't actually look like this in real life. We're in something called plane space. But ultimately, we sort of have a range in one dimension from x equals 0 to x equals a, these 2 points. And the particle, whatever it is, it's subatomic, maybe an electron, can be anywhere in this box between x equals 0 and x equals a. Now, inside the box, anywhere between these two vertical lines, anywhere in the box, the potential energy is 0. Okay? The potential energy is 0, which means the particle can move freely inside the box. Now, that does not mean that the particle can be equally likely anywhere in the box. There's actually, what we're going to find is, depending on the energy level, you can actually have particle maybe at high probability in the middle, and maybe 0 probability at these ends right here, or it can actually be equally probable at 1/4 and 3/4 of the. I mean, that's not the point. The point is that the particle can just move freely anywhere here. Okay, no potential energy. Now, the way to think about it is like, if the particle is in here somewhere, these are like walls, but the walls are infinitely high. So you could travel the entire existence of the universe up this wall and never reach the top, because there is no top. It's infinitely high. And what that's supposed to sort of mean on a physical level is that the potential energy at the wall, literally at the wall, and then beyond the wall on either side, is infinity. So in theory, because the potential energy on the wall and outside the wall is infinity, the particle is confined inside the box. Confinement, recall, results in quantization. So the particle can never leave this box because the potential energy to leave the box is infinity. Okay, it can never leave. And the particle is somewhere in this box at some probability, depending on the energy level. All right, so a way of saying this is when x is less than or equal to 0, so over here, potential energy is infinity. From 0 to a, in this region, the potential energy is 0, and then for x equal to and greater than a, potential energy is again infinity. It can never leave the box. Well, we're going to use that to our advantage and we're going to essentially solve the Schrödinger equation for the particle in a box model, and we're going to do it with the assumption that the potential energy in the box is 0. Okay, so how do we do that? Well, we just said that potential energy in here is 0, so that's going to greatly simplify things. This is 0. Okay, we don't even have to worry about the potential energy term. So our expression becomes negative h squared over 2, negative h bar squared over 2m times, it's ultimately going to be, and I actually neglected to draw this, this is the second derivative with respect to x of xi, which is the wave function, has to equal the eigenvalue, which will turn out to be the energy of the particle times the wave function. So we need to know what the wave function is. The wave function we're going to use for particle in a box is going to be a times the sine of n pi x over little a. Okay, a is just a coefficient that we're going to use. Okay. So what I'm going to do first is I'm going to differentiate xi with respect to x. So if I differentiate sine, this is going to be chain rule. Derivative of sine is going to be cosine of n pi x over a, but I have to multiply times the factor by which x is multiplied, which is n pi over a. So that means this is going to be a times n pi over a times cosine of n pi x over a. That's the first derivative of the wave function xi. But notice in the Schrödinger equation, I need the second derivative. So the second derivative of xi with respect to x, if I differentiate cosine with respect to x, that's going to be a negative sine of n pi x over a, but I have to also multiply again times this n squared, or by this n pi over a, and if I multiply n pi over a times n pi over a, it's going to be n squared pi squared over a squared. And I have to keep this negative sign over here. Okay? So ultimately, when I rearrange this into the form I really want, this is going to be negative n squared pi squared over a squared times a sine of n pi x over a. All right? And another way of saying this is to notice, these are kind of important things to notice because they're really important. What is a sine n pi x over a? Just this part right here. That's the wave function. So I could just jump and just say, replace that with xi of x, right? That's just the wave function, right? So that's why I have this here. I kind of dropped the a sine n pi x over a, and I just have negative n squared pi squared over a squared times xi of x, all right? So a way of essentially writing this, now what I'm going to do is I'm going to take the second derivative of xi with respect to x, what I just found, which is this, and plug that in here. Multiplied by negative h bar squared over 2m, that has to equal the eigenvalue times I of x, all right? So I'm going to keep this negative, remember h bar is h over 2 pi, right? So suppose I square both sides of this. Then this has to be h squared over 4 pi squared, right? Hopefully that makes sense, all right? So when I do this, I'm going to keep the negative sign. I'm going to have this h squared over 2 pi squared. Here's the 2m. I'm going to drop the 2m down there. And notice what I'm going to do. This part right here, I'm going to circle this in light blue. This right here, this was essentially what I just found as part of the second derivative of xi with respect to x. I have this negative n squared pi squared over a squared, and then times a sine n pi x over a, which I recognize as being xi of x, right? And that has to equal eigenvalue, which is the energy, times xi of x. What you're allowed to do now that you've gotten rid of the derivatives, since you have the derivatives there, you can't do anything because the derivative is an operator. You can't cancel a function out of an operator. But once you've done the operation, if the function still remains on both sides, what you are actually allowed to do is divide both sides by the same thing, which in this case is xi of x. You're allowed to divide both sides by that, and notice that xi cancels. So what you're left with is the e. I'm going to go ahead and write this. This e is going to be equal to negative h squared. This should not be h bar. That should just be h squared. Negative h squared times negative n squared pi squared. Just rewriting what I have here. Over 2 pi quantity squared times 2m times a squared. Now that's a kind of a mess. Let's go ahead and simplify it. And we actually get this up here. Notice that the two minus signs cancel, so it becomes positive, which is what we expect. We get h squared n squared pi squared over, if I square 2 pi, the quantity, this is 4 pi squared. So this is 4 times the 2 right there becomes 8, pi squared ma squared. The pi is on both sides, so pi squared cancels, and you are left with the energy of a particle in a one-dimensional box. It is h squared n squared over 8ma. This, notice I circled it because it's very important. This is an expression for the energy that you need to memorize. Okay? On an exam, unless they ask you specifically to derive this expression, there's no time to just sit down and derive this. I've done it so many times that I'm proficient at it. If you're first learning this, you should know where it comes from, but you should just memorize the energy due to a particle in a box. Okay? When we do this for particle in a 2- and 3-dimensional box, we're going to have kind of the same thing. We're just going to add things sequentially onto it to get the total energy due to 3 dimensions. Okay? But you're going to follow the same logic here, even for deriving this for 2 or 3 dimensions. Okay? So hopefully this makes sense. You kind of understand the implications of where this comes from. One thing I do want to point out, though, from the Schrodinger equation, if you assume that the potential energy is not 0, then you can't, in other words, if the potential energy in here was not 0, then this thing doesn't go away. Okay, it doesn't go away. And there's actually another form of the particle in a box called the finite well model. This form where we have potential energy going to infinity on either side, this is called what's called an infinite potential energy well. Okay, my pen's kind of messing up on me. Infinite potential energy well. All right. If you have this not go to infinity, like it's a finite number, you don't even have to specify what the number is, just knowing it's finite. Then you call it a finite potential energy well, and the derivation becomes a little bit different. But it's still doable from what you are able to do, and we'll do that in a separate video. But this is particle in a box, derivation for energy, for an infinite potential energy well. All right, so hopefully this derivation made sense. In another video, once we go over the other models for particle in a box, we will do some calculations with this. So I hope this helped. See you in the next video.